The problem statement says to find the interval and radius and convergence of the summation from n equals 3 to infinity of negative 2 to the n times x plus 3 to the n over the quantity n times the square root of the natural log of n. So basically what we need to do first is use the ratio test. The ratio test states that the limit as n approaches infinity of an plus 1 over an absolute value that is less than 1. And so from that we can both get the radius and the interval of convergence. So we would treat this as a sub n, and all the variables n, we can add 1 to them to get this ratio test thing. So the first thing that we would do is take negative 2, make it n plus 1, x plus 3, make it n plus 1, and have it over n plus 1 times the square root of ln of n plus 1. And then we multiply by the reciprocal of this, because that's equivalent to just putting it over the part a sub n. And so we can say negative 2 to the n, that goes in the denominator, negative 2 to the n, x plus 3 to the n, and the square root of ln of n. So that's all absolute value, and it's the limit as n approaches infinity of that. And so what we can do, the cool thing about this is if n plus 1 is in the power, we can just multiply by whatever's inside again and then subtract 1 from the power. And so what we'll get is negative 2 times negative 2 to the n times x plus 3 times x plus 3 to the n, and then we can have that over the same, and these are the same, and so this gives us the capability of canceling out x plus 3 to the n and negative 2 to the n. Also, because this whole thing is absolute valued, we can get rid of the negative sign on any of the parts of the equation. And so we can get rid of this negative, and then we're left with the limit as n approaches infinity of 2n square root of ln plus ln times n times x plus 3 over n plus 1 square root of ln of n plus 1. And so from our knowledge of taking limits in previous classes, we can say that because the coefficients of n are equal to 2, if you divide them, we can just say that these terms go to 2, and then because the coefficients here are the same, we can say that these terms go to 1. And so this leaves us with the limit as n approaches infinity of 2 times x plus 3, and so the limit goes away, is less than 1. And that leaves us with x plus 3 is less than 1/2. So this right here says that our interval of convergence, because it's in this form, our radius of convergence is 1/2. So now that we've found the radius of convergence, we need to go about finding the interval of convergence. And because this is an absolute value, we can actually split it up into two inequalities. We can say x plus 3 is less than 1/2, and that is greater than negative 1/2. And so we can say that 3 is equal to 6 over 2. We subtract 6 over 2 on this side, and we say x is less than 5/2. And then we subtract 6 over 2 on this side, and we say x is greater than 7/2. And so from that, we have our interval convergence. So this right here is equal to I. Then, after this, we need to make sure that the bounds are valid. And so basically what we do is we say that the value negative 7 over half, we put it in to our original sum, and if that works out in the sense that it converges, then we can say that it's part of the interval. And the same for negative 5/2. So let's do negative 5/2 first. If we put negative 5/2 in here and add 6/2, we're going to get 1/2. And then we multiply that by -2, and we get -1. And so we'll have our sum will be sum from n equals 3 to infinity of -1 to the n over n times the square root natural log of n. So to find this sum, we first use the AST, the alternating series tests. To use the AST, first we have to make sure that it's, first of all, decreasing. And the way we do that is we say that -1 to the n plus 1 over n plus 1 over the square root of ln plus n. Sorry. The square root of ln of n plus 1 is less than -1 to the n over n and the square root of ln of n, which is a true statement because the denominator is so much bigger than the numerator. So that's our first condition. Our second condition is that the limit as n approaches infinity of this term here is 0. And because the denominator is way bigger than the numerator, we can automatically make that assumption. So, and then obviously the last condition is that it's alternating. And so we can do the alternating series test. Basically what the alternating series test says, the first step is that if the limit as n approaches infinity is equal to 0, the absolute value of this, then we can say that it conditionally converges. And so we'll write the limit as n approaches infinity of 1, because it's the absolute value, of 1 over the quantity ln of square root of ln of n is equal to 0. And we can make the conclusion that it conditionally converges. So in summary, -5/2 checks out. Second thing we need to do is test -7/2. So we'll put -7/2 in here. We add 6/2, which gives us -1/2. And then we multiply by -2, which gives us 1. And so our new sum is the sum from n equals 3 to infinity of 1 over n times the square root of ln of n. And this is different because we can't use the alternating series test, so we need to find another way to find its limit. Or not find its limit, but find the sum. And so what I would do is use the integral test. The integral test, basically, the three conditions are that it has to be positive, it has to be decreasing, and it has to be continuous. So for continuous, we know that both n and the natural log of n are continuous functions, so we can make that assumption. For decreasing, as stated here, because the denominator is so much larger, we can do this exact same concept. And for positive, there's no negative values because there's no negative terms in the sum. And so we can go about doing the integral test. Basically, we just take the integral of these bounds of a sub n, and so we can say the integral from 3 to infinity of 1 over x square root of ln of x. And so we'll use u substitution because there's ln of x and x, and so u is equal to ln of x, du is equal to 1 over x dx, and so we get the integral from 3 to infinity, or sorry, we won't make this, we won't put bounds yet, but we'll say the integral of 1 over u du, and when we integrate, we can say ln of u, which is ln of x, from 3 to infinity. And then once we evaluate the antiderivative, we say, because ln of x goes to infinity, it's infinity, ln of infinity, and so we just say infinity minus ln of 3, which becomes negligible because the infinity takes over. And so that goes to infinity. And basically what the integral test test tells us is that because this goes into infinity, the series itself goes to infinity. And so, this diverges. Then, in the end, we can define our, finalize our our interval of convergence and say that it doesn't include -7/2, but includes -5/2. So when we make our final conclusions, we can say that the series converges for x is greater than 7/2 and less than or equal to -5/2. We found that it's less than or equal to -5/2 because the series converges at -5/2, and we found that it's greater than -7/2 because at -7/2 it diverges. And this also means that for any x value in between these two values or equal to this value, this whole series will converge. Also, the conclusion that we made was that the radius of convergence is 1/2. Basically, that means at the center, x is equal to -3. We can go 1/2 higher and 1/2 lower, and that's basically what defines where we converge. Thank you for listening to my video. Come back later.
It's not letting me stop.